So this is the example last week we discussed. We have the linear black hole, and actually we want to have the generator G. And how to have this G? So later we will write this G. But currently if we want to have the G, in fact we need to have the co-generated polynomial. So this is given. Given the co-generated polynomial G of x for this black hole, 7-fold, 7 equal to n, so it's 7. And for its k. Therefore, we have 3. Alright, so we have the specified co-generated polynomial. And actually, we want to have the derivation for g. So this is the goal. Well, of course, we can specify all things in terms of polynomial, but later we want to have the matrix operations. Well, so we have these. We need to find polynomial, and so that the polynomial can be represented by the vectors. Well, so P1 actually from 3, so it's up. So we have R. Starting, so we have the first one. Here we have XR plus K minus 2. So we have 1 to K. Alright, so we have 1 to K. And actually you can check it later. We have the polynomial x raised to power to this. And divided by the current polynomial, generated polynomial. And we want to find the remainder. And remainder here we have 1 plus s. So we have the increasing order. Increasing order, let me check. Yeah, increasing order. So increasing order, 0 and then 1 is 2. So degree of the polynomial is 3. So of course the remainder we have degree at most is 2. So we have 0, 1, and 2. So later you can check it. Is it true? So this one, finally we have the modular 2 addition. So finally we have this remainder, and this remainder mapped to 1, 1, 0. And likewise this 0, 1, 1, and the others. Well, that's on the vector. So we have the parity check matrix. So here, parity check matrix, we have this P1, P2 to P4. So this is parity matrix. So finally, we have G forms by identity matrix concatenated by parity matrix. So we will have this G. And so that we will have the index I, actually it's K by K. And P actually is K by R. Alright, so we can have the dimension. I is K by K dimension, P is K by R dimension. And so that we can find out the way to have the G. In fact, we use this way. And maybe you think, okay, why we have this? Later we can have the manipulation to let know if we have the given distribution. And so that we can have the G. And once we have the G, we can pass on the matrix operation to have the vector, the co-vector. And later we can show you the co-vector. But let me start here to let you think about this and talk to your neighbors. Oh, okay, this is a procedure to find the so-called generator G. So how to have the generator G? Look at this. And also you can check. Maybe I ask, good one check, is it true? The remainder, and good two. Good two, you can check the second vector. polynomial. Group 3, this one. And group 4, check these. Alright, so allow you to have 2 minutes to think about this and also check with your neighbors. And you can get closest. And the group 3, maybe group 3, maybe rearrange the seats. You can fast or get closer. Rotate and fast. And same for group 4, you can rotate and fast.
So the focus at P40 was RP, and what's the RP is?
Maybe you can discuss yourself, or maybe you can join us. So first of all, can you make sure the polynomial of method here, group 1, yes, right? And the group 2, yes or no? Not finished? You can check it. Using exclusive or addition. Exclusive or, right? And the polynomial 3 by group 3, yes or no, yes. And group 4, yes or no, yes. Alright, so I think, oh yes, but you need to know, okay, how you have it. The addition here. This one. Alright, so we use module to addition. If we have one of ones and then we have 1, or otherwise we have a 0. So the best sum is this addition. And so then finally we have the results here. If so, then we can have the generator G. And maybe you have a question, why G follow the form here, I and P? So later we can let you know what we want to have. Name for P, we call it parity matrix. For I think you understand the meaning identity matrix. So actually what we want to do, we follow the way, we there you have a message. Messaging is 1 to K. And the messaging multiply G, then we will have a data. So this one should be the original one. And this is the parity. Alright, so this is the parity. So if we have N, follow I and P. So finally we should have the result. Oh, it should be N and NP. And of course this is M again. And this is parity. So N multiplied results in parity bits. For this purpose, we want to have the position for I and P. And the resultant vector should be message again, but this one related to parity. So we want to have the resultant bits follow the pattern, original message, and then parity bits. That's it. So that's why we want to use this way to construct G. Alright, so G follow the way, so it's G. In fact, we should let it know first. And then we have their way to have G. But after that page, we have the discussion. So it is somehow late, but it's still okay. We let it know, oh, okay, G we want to have the form like this, and so that we can generate data plus parities. Well, so that's it. So we have this. And once we have the vector here, it's the resultant whole vector. Whole vector. Alright, so this is a way to have G. So in fact, even polynomial, if we want to have the easier way to have the calculation, we want to have vector or matrix. So here we have the matrix to let us have the vector. Once we have the vector, of course we can convert it to the original way to show the result. But even in polynomial, it's a way to express how to have the further operations. Well, so we have N, we have G, and the covector we just use C. Alright, so the resultant notation, we call it C. So we have the operation C. C actually 1 to K, actually it's message 1 to K. And the others actually, you can mess up the manipulation. We have the exclusive addition, so it should follow the form. And in fact, this one we can express in terms of matrix. So here, C K plus 1 to Cn, actually it's N multiplied P. So that we have the current result. And then we have the corresponding parities. Alright, so this is operation. We want to have the resultant covector. And finally we have the form again. You see? Actually we have a message N. And message N actually follow the way to have the individual bit 1, 2, 3 to K. And here C individual bit 1 to K. And C K plus 1 to Cn. And please see that C1 to Ck actually identical to message. And the remaining one, we have an operation based on message and polynomial the parity matrix. And so that we can have the corresponding operation for Ck plus 1 to A. Alright, so we have a margin to addition to have the results. So we reset what we want. C, follow the way N multiply G can have the whole vector. And actually G follow the form. I should be K by K and P should be K by R. So finally the dimension should be K by N. That's it. Alright, so this is G. So if we want to have the clear description, we should have this. G actually equal to I is K by K. And here, P is K by R. And so the resultant dimension should be K by N. Alright, that's all. So we have the way. And we rewrite the previous way how we have the result. Oh, okay. Polynomial p sub I, how to have that one? Actually, we have r plus I minus 1. So first one, actually minus 1, so we can start from 1 to k. So originally we have 1 to k. That's correct. So this is the previous operation. We use this, but right now we rewrite it. Something like, oh, okay, we summarize the polynomial follow the way to have the remainder, and so that we can have the hierarchy matrix. So up to now, almost the same story, but we emphasize. Well, if we have a P parity matrix, actually we can have the next matrix, this one. So this matrix later we can have a different story called syndrome. Syndrome later we can then know, oh, okay, it's someone to show, oh, okay, something wrong. But this one later we will show you. Up to now, check before matrix H. Up to now, everything's okay. So let me check quickly. Oh, maybe for me it's hard to memorize your name. So maybe can you measure your name? William. William. Yeah. Okay, William. And you should be
Gabriela.
Gabriela. William, Gabriela. So any questions? No. And Gareth.
Yes.
Yeah, Gareth. Gareth. Yes. Gareth, any questions?
No.
And for you, it should be Thomas. Oh no, I failed to notice that one, but I tried to know your name, Thomas. That's correct. And maybe first time to ask you your name in English? Grayson. Okay. Maybe next time I may ask you again, Grayson. Okay, so at least up now, any questions? And you should be J, right? Okay, and you? Doria. Doria. Okay. So if no question, this is a story. And then you have 1 minute to keep all things in mind. And later we can have a different story, H. Alright, so 1 minute to keep all things in mind, and so that you have the way to find G. Alright, actually G coming from P. So I get back to the previous slide. So something like this, starting from this page. Actually, the previous example asks you to have a P. So we have a P having check matches, and so that we have G. So G, so that we have a C. So that's the story we want to have. So almost 1 minute, so let me continue. Here we have H. Currently, maybe this way, it's hard to memorize, perhaps we have transpose H first, and then we can have P and I is R. So identity matrix with the dimension R by R. So this one, the same, right? We have a G equal to this, we have the weight, so up now the same. But right now we want to do something like this. We want to have the calculation for H. Previously we have H without transpose, but right now we have H transpose. H transpose actually is P first and then here we have identity matrix R by R. And here is P by R. So that we have A by I. Alright, Right. So this is I expect this one. Rather than the previous one, we have H transpose found from here. And actually G, no problem. And we can pass a hierarchy matrix like this to have the transpose matrix H. And why we want to do that here? We can have the generator matrix G through the air, and so that we can receive it. And receive it there, we have a C. And C right now, we have H transpose there. And we want to mess up H transpose there to have the further manipulation to check. Oh, finally, should we have a zero vector? So it's null vector. So can we have the null vector? First of all, think about this. We have a C and the new notation. Because of parity, so we can call, oh, this is a vector. It's called parity vector, so we have a C sub P. And C sub P, previously you know, it should be M multiplied P. That's correct, right? If so, then we can continue. We have an H transpose, and the H transpose defined by these. And right now we want to have a C H transpose to have the multiplication, so we have these. So it should be these. It should be these. So let us check it first, sorry. So it should like this, so maybe not remove this. So we have this again. And right now, this is P and M and this is. So finally, we have the operation MP. Addition is exclusive of, and the CP and the I identity match R by R. And this one is CP. And this one is CP. And the best exclusive operation CP plus CP should be 0. So finally, we have a 0 vector. So because of this, we expect to define H transpose. So previously I forgot, we still have H transpose. So finally, we want to know H transpose rather than H itself. So it doesn't matter, we want to have this. And because we want to have this, finally we should have a 0 vector if everything is okay. If everything is okay, so that says, oh, everything is okay. Finally, after checking this, well, if nothing wrong, it should be null vector. That says it should be a 0 vector. If it is 0 vector, then we cannot tell anything wrong. We cannot tell anything wrong. So indeed, is it possible to have something wrong? If we receive a 0 vector, it seems to be, oh, we expect 0 vector. We cannot tell anything wrong. But is it possible to have something wrong? Yes. It's possible to have something wrong, but finally, okay, since we cannot tell something wrong, so finally we just follow the principle. 0 vector, then we think nothing wrong. However, if it is not 0 vector, can you tell, okay, nothing wrong? No, right? So, non-zero vector indeed, we know something wrong. So we can use this principle. Oh, okay, non-zero. So that we can know, okay, something wrong. But 0 vector, we still think, oh, okay, maybe nothing wrong, but we cannot tell anything wrong. Alright, so we want to pass on this principle to have the judgment. So we have these. I want to show you this. Okay. Here we have the syndrome. Actually, for the real operation should be the receive receive vector has its covector plus arrow. If a covector plus arrow, and then we should have these. The individual one, so we have a C multiply H transpose and arrow multiply H transpose. So fine, we just have an arrow multiply the transpose factor H. Therefore, we have arrows. But look at this. E multiply H transpose. Is it possible to have a zero vector? It's possible. But if not zero vector, then we think, okay, something wrong. We got it, right? So here is idea. Okay, if not null vector, then we got something wrong.
Sorry, what does the X in XHT stand for?
H.
Yes.
H is X or H.
X.
X actually we have the covector through the air and received by the receiver, so that we still have the actual arrow possibility. So original one plus the arrow possibility, and where we have arrow here. C originally, right? And we have arrow here, so that we have a C plus arrow is equal to X.
Oh, okay.
The receive vector.
Okay.
So we have these. So the real one should be we have the arrows. So finally we have that. If we have that, then so the previous one actually that term we call is syndrome. So syndrome, if Taiwanese want to know, oh, what that means syndrome. Maybe because of poor article, so I should disable and then I can pick up the hyperlink. Finally, I know the reason. So sorry, maybe Christy, you have the hyperlink right here. Syndrome, right here. So we use that one to serve as a syndrome. And again, we have a G and H. So look at this. G and H, actually we have an H transpose first. So we have a P here, right? And then H transpose to have these. You can check it, is it true? So write this first and then you will have H. So you can check it, is it true? So 1, 1, and here is IR. So finally we have transpose, so we have a 1, 1, 1. And finally transpose, we have a 0, 0, 1. Is it correct? And we have a vector 1, 2, 3, 4, and then we have a 7. So 1, 2, 3, 4, 5, 7, right? So it's correct. So I expect to have this result. Alright, so P first and then this one. We derive this result and then we can derive H. But actually, once we have H, we still need to have the operation of transpose. So it won't be necessary to have the transpose. I guess so. So we can have the results. Alright, so we have the results here. Maybe we have a method 1, 0, 1, 1. So right now, C multiply G, we will have the results. The path fits here. And right now, if no arrow, actually we should have S equal to C. So finally, yes, it's true. Syndrome is 0 or null vector. That's correct, no problem. However, how about if we have an arrow, right now maybe arrow follow the phones here. Okay, just one big arrow here. We have a 0, 0, 1 and the other 0 again. And so that we have x equal to the vector. And then syndrome is non-zero. Yeah, non-zero. So the syndrome, then we have this. Oh, sorry. This one correctly, but before that one, look at this. Previously, we have this. It's this is S. This is H transpose. And this is the syndrome. And the syndrome here, 101. 101 can be found by checking H transpose. Which position? This one. So it's a third position. Through the operation, someone like, okay, actually this one wants to get the third position. So finally we have the syndrome equal to the third position. Oh, okay, we can reverse it. Oh, we have the syndrome, you can find which row. Okay, it's the third row. Because of a single arrow, so based on this, syndrome can be mapped to the arrow position. Once we know all this bit with arrow, so we should have the third bit. So this one, 1, 2, 3. 0 should be corrected to 1. So finally, through the third position correction, so we have 1, 0, 0 corrected to 1, 0, 0. Alright, so the current page we want to let you know the story. The syndrome exactly reflects the pattern, and this pattern reflects where to have an arrow. 1, 2, 3, it's the third position. Oh, okay, it's the third position. So we know, oh, third position calls the arrow, so we can replace 1 by 0. So if we can replace, oh sorry, it should be 0 replaced by 1, and so that we have 101, and so that we have the remaining bits. So if we assume just a single arrow, this single arrow can indicate where to have the arrow. Alright, so that we can have the correction. And maybe you think, okay, how about more arrows and then we still have the other way? No, just a single arrow. If we have a single arrow, this is the way to have the correction. We can pass on the signal to find the position. And once we know the position, we simply need to correct the corresponding position. Oh, 1, 2, 3. So this B should be corrected. So we have the corrected vector. Alright, so this is the story. About the story, check it. Then you have 2 minutes to discuss with your neighbor. If any questions, then you can let me know. So okay, all right. The position. We just reverse and so that we have the story. try to extract the raw value to the outside environment.
Oh, I thought it was like 14 dimensions.
One of So Sue, is it okay? You know the story? And Alice is your name, right? So I understand the story, right? Or maybe ask Sue to let you know the story. So Thomas know the story, right? Thomas, am I right? You know the story, right? Or maybe you don't know. Actually, the story is 001. So multiply means 0. Oh, sorry, here. 001. So multiply, we want to extract this. Extract this, so we know, okay, because of the third position. So that we just count, okay, using the pattern. Yeah, it's the third position. Yes. Because of this, it's this one. Multiply this edge and this one. Multiplication, so extract this one. This one, this one. So finally, extract that vector, that row vector, so that we can use the resultant row vector to serve as a syndrome, to serve as a pattern. So Jen, right? So you can get closer to have a discussion and try to catch up on the current discussion. So finally, understand why the pattern can find the position of the arrows. Because of the multiplication, E multiply H transpose. So this is the color vector. The color vector multiply the vector here. 0, so no, only notice 1. So 1 can extract the current bit. Likewise for the second row, extract the bit. The third row, so the third column, extract the bit. So finally, extract the third vector, 101. And so, okay, all right. So you can have the operation, but finally notice, oh, which one? Based on the pattern, 1, 2, 3. Oh, sorry, it should be this one, 100. Okay. Not this one. 1 or 0. No, because of this pattern, so we know 1, 2, 3. The third bit should be wrong. So the third bit should be wrong, then we should correct. Should be correct, so 100 should be corrected to 101. That's it. So the curve patch wants to tell you know the story. The syndrome can reflect where we have errors. That's it. So this is the color of okay? So one more way to discuss and so that we can go to the next page. Here, something wrong, so we should have the correction, not this minus 2. Alright, so let me move on to the next one. So let me make sure. Let me start. Yeah, this one. Sometimes the system has something wrong, so I need to enforce it. Alright, tackle rest.
Yes, because you have to move forward. Yes.
So actually we should have this question first. For the previous discussion, any questions? And show me your status, yes or no. Or maybe let me make sure. Can you see, Thomas? No? Okay. Alright, use this one. So currently no. Okay, that's good. So not finished? Okay. I will finish. Sorry. Not finished, raise your hands. Okay, I will finish, so let me go to the next one. So today we still have the good discussion talking about selected problem for exercise, self-exercise number 1. So we have three questions. First one, second one, and the third one. Alright, so right now let me have the assignment. So, good one, checking A, B, C. Alright, and good two, checking B and E. Good two, Jen, B and E. Alright, so at this type of picture for your problem. But finally, I still expect all of you can have your answers. And this time, I will use a different tool. Later you will know that one. So, good 3. Problem 2.21. And good 4. This problem. Alright, allow you to have 5 minutes to check the problem. And later, we will have the presenter from good 1, good 2, good 3, and good 5. 5 minutes for checking the result. Then you can use any tool. Of course, once you have a tool, you should understand the meaning. But this time I have a new tool, this one. Sorry, now this. Sometimes something wrong. This one. Alright, so we have the problems on handling. Problem 1, problem 2, and problem 3. And actually you can reply so that it will follow. And so that it looks like this one. For example, oh, okay, let me try to have a different one. Oh, sorry. It should be this. Let me try, so anything wrong? Maybe not this, let me try it again. Oh, okay, that's right here. So, let me have the demonstration. Oh, okay, something like this. I use this account. So, I use my different account on this one, serving as a student. So you can register serving as a student, so student here. And then I can have the different answers. I just try to have the text. And so that you can have a video. You can have a photo, you can have text or anything, you can have the others. So you can try. So why not? You can try to scan the QR code. Alright, so you can try to scan the QR code here. And you can use cell phone. If you use cell phone, maybe next time can you use tablet, I'm not sure. So Jan, this time, this one, you can have the answer properly because you failed to have the answer online, so you can use this. But registers using Google account. You can use Google account registers. So later, let me make sure presenter from group 1 this time. Who will be the presenter? The presenter needs to show your result on Padlet. And the group 2 this time, who will be the presenter? This time, allow you to you try this. But you need to let us have your answer there. Yeah. And good 3, sure. And good 4.
I can do it.
Sure. If so, then I wait for you here. If you have your answer, you will follow me.